Can you see my presentation? I cannot see you anymore, but it's fine. Okay, great. So thank you very much for the introduction for me and for inviting me here. This very cool conference. So before going into the core of the talk, just a shout out of this being an ongoing collaboration with Alin Al-Bushaffer and all his group. So the work that I'm going to present has many of my work, and I believe many of the works that we are going to see and we have seen at this conference inspired by nature, by the amazement that we prove every time we look at animal kingdom, and more specifically here about the capability of humans and other animals to perform periodic motions, natural and periodic motions, a very efficient and an effective way. So as we know from decades of studies in biomechanics, and these capabilities are strongly mediated by the presence of elastic elements together with inertia elements in the body of our animals, like tendons and muscles. And this is clear intuitively if you think about linear modal analysis. So, for example, if you just put a mass together with a spring, what you get is open loop oscillations. This was one of the big reasons why we started, people started putting elastic elements and soft elements into the body of a robotic system, leading to what someone nowadays call soft robotics. You can see just a bunch of nice examples here. However, we have all these very cool structure. But what happens if you already in simulation, if you try to take a very simple mechanical system with some elasticity, like the one on the right, is that the kind of oscillatory behavior that you find if you just initialize the system in some initial condition and leave it be, are quite different from the expectation, the controlled oscillations that we observe in animals, and it are more close to chaotic behaviors. The goal of this research is to look for the needle into haystack of looking for regularity, but open loop regularity into this haystack of chaotic behavior that we find in mechanical systems. And we do that with a framework that we call controlling eigenmanifolds, and let me try to convey the basic ideas of this framework in a few minutes. So what we do is that we divide the design in two steps. The first one is about analyzing or understanding what the robot can do well. So in terms of its mechanics, what it can do in terms of oscillatory behavior. And we do that by extending the very linear model theory that I used at the beginning of the talk as a kind of intuition. So in linear system, you have all these eigenspaces, one for each degrees of freedom. An eigenspace can be seen as an infinite collection of periodic orbits with an open loop, and they start from the equilibrium and are self-similar, and you have one for each energy level. When you move to a nonlinear system or with some like a non-Euclidean matrix driving it, what you get is that this configuration, the state space gets curved, and as a consequence, we see that the eigenspace gets as well curved into a manifold, so a 2D surface, but still it maintains all the essential characteristics that I described before. So, for example, being an infinite collection of self-similar oscillations with open loop oscillations at different energy levels. Instead of going on the nitty-gritty of the mathematical definitions of this object, it's probably more interesting to look at some example just to get a grip of what these eigenmanifold represent. So this is one of the two eigenmanifold of inverted double pendulum with some parallel elasticity. And what you see here are three nonlinear modes, so three slices of these eigenmanifolds for three different energy levels. So what I want to stress, these are, once again, these are completely open loop oscillations. And you can look also more complex, high-dimensional mechanical system, like for example this KUKA robot with where we add some parallel elasticity to it. What I'm showing here is all the 7 eigenmanifolds of this robot, so 1 for each degrees of freedom, but I'm just showing a slice, so for 1 energy level, 1 joule. So once we have a way to define what a robot is good in doing in terms of oscillatory behavior, the second step is to design controllers to sustain and excite these capabilities. And we do that, we're supposed to do that with 2 nested control loops. One is about stabilizing the eigenmanifold, so once you select one of the eigenmanifolds connected to some behavior that you want to generate, and then you make it an attractor by means of feedback control. And then the other is an energy regulator that keeps the energy constant in the system and allows to select the desired oscillation among the infinite ones that you have in your eigenmanifold. So this is the theoretical foundation of at least of this theory in a nutshell, but as robotics is what we have been very particularly interested to understand if we can use these things to generate these intelligent behaviors by exploiting the mechanics. And we have been looking in 2 directions, just showing one example for each of the 2 directions. One is industrial-like motions, repetitive motions, and what you see here are some videos of the many in which we are stabilizing and also switching from one of the others, the very nonlinear oscillations that I was showing before of our elastic KUKA robot. And you can imagine to use them to perform tasks like painting or whatever. The other one is, of course, locomotion. You've already seen quite cool talks about this topic today. Let me start. Okay, it's not. Let me try to see if I can. Okay, it worked. So let me start with a simple example. We have this leg you have lumped elasticity in the 2 joints of the leg, and again we use the same framework to excite these swinging motions that come out to be a eigenmanifold of this leg. You can do that for different energy level, and what it's remarkable is that if you do that, the closed loop behavior that you get is remarkably robust to external perturbation. The reason being, at least in our interpretation of it, that we are not, as in standard nonlinear control, forcing some prescribed behavior on our system, but quite the contrary. We are just helping the mechanical intelligence of the robot being expressed. And moving to actual locomotion, we were recently able to combine multiple of these eigenmanifolds in a fully hybrid setting to obtain modal forward hopping using nonlinear modes, and you can modulate the energy of these modes to get different velocities of locomotion. And it's just a sneak peek of some current ongoing research about performing similar tasks, but with a more complex soft robotic structure. To conclude, we are also working on a MATLAB toolbox to automatically extract all the eigenmanifolds of a mechanical system expressed in your favorite way with your def equation or directly with the CAD. And we are hope that we'll be able to make it release it openly in a few months. That's all on my side. Thank you very much for your attention, and I look forward to the panel discussion.
Okay, thank you, Cosimo. This is a really great overview of your work. Just a quick question. So your mechanical dynamics is mostly about the mass and the elasticity. These are is there any other components you're thinking about?
I mean, in order to get to generate oscillation, yes, we are mostly focusing. I mean, you need what you see from the theory is that you need some way to store kinetic energy and some way to store potential energy. So we focus on springs, which just, I don't know, maybe they're just easy to implement, but you can think of any way of storing potential energy, like magnetic field or other crazy stuff. And in principle, you should be able to obtain similar results.
Excellent. Yeah, thank you. This was a really great introduction of your latest work. So let's talk about it in a few minutes.